All right, so we're ready to talk about the final topic of this course, and that's Stokes' theorem and the divergence theorem. And the good news about Stokes and divergence theorem are that if you really understood the two different versions of Green's theorem, the circulation version and the flux version, Stokes' theorem and the divergence theorem are just higher dimensional analogs of those two theorems. So let's talk first about Stokes' theorem. So recall that when we learned the circulation version of Green's theorem, it related the curl of a vector field in the plane to the line integral or the circulation integral on the boundary. Well, Stokes' theorem is going to say exactly the same thing, except it's going to be for a surface in space. So here's my surface. That I'll call S. And notice that for a surface, assuming it's bounded and oriented, that's going to be important. We want to assume that our surface is going to be oriented. It's going to have a boundary curve that we'll call C. Now what we need to do is we need to give an orientation to C. And the convention we're going to use is that if I look at a point on the surface and look at the normal direction, I'm going to pick the orientation of the surface to be up. So in other words, the normal direction of the surface is going to be up. And then the curve I'm going to pick to have a counterclockwise orientation relative to the orientation of the surface. So in other words, if I look down, straight down on the surface, it has a counterclockwise. The curve has an counterclockwise orientation. So yeah, so we're assuming that S is oriented. And we have this oriented boundary curve. And of course, we also have a vector field that's defined over this surface and the boundary curve. And so what Stokes' theorem is going to say is that if we integrate essentially the curl over the surface, that's going to equal the circulation on the boundary. It's really the same idea, like I said, as the circulation version of Green's theorem. So let me just write down what Stokes' theorem says. It says that if I do the surface integral over S of the curl of F, and now the curl of F in space is going to be a vector. And what I want to do is I want to take the component of that vector that is lying in the normal direction. And so here's my normal direction pointing upward like that. And I add up the contribution over each little piece of the surface or the surface elements. That's going to equal the circulation integral along the boundary. And now up till now, we really talked about circulation integrals in the plane, but circulation integrals in space are exactly the same thing. We just have a simple closed loop in space, and I just integrate the component of the force that's pointing in the direction of the curve. So this is what Stokes' theorem says. And again, we can think about this in a picture. So everywhere on the boundary of the surface, at each point, I can measure the rotation of the vector field by how much it curls at each point. So that's the curl. So if I add up all of the curl on the surface, somehow that should equal the total circulation around the boundary. So if Stokes' theorem is the higher dimensional analog of the circulation version of Green's theorem, then the divergence theorem is the higher dimensional analog of the flux version of Stokes' theorem. And in fact, we're going to sort of redefine our notion of flux. So the flux of a vector field over what's called a closed surface. And now what I mean by closed surface is a surface that's actually the boundary of a volume region, like this. So you can just think about a cube. So the flux of a vector field F over this surface that's closed, that's enclosing a volume region, is given by, well, just the surface integral. But we're going to give it some special notation. Okay, so we're going to do a double integral with a circle around it to signify that the surface is closed of what? Well, what we're going to do is we're just going to take the component of the vector field that's in the normal direction. So essentially, pictorially, the part of the field that's going straight out of the surface, like that. And of course, integrating over the various surface elements. So the flux is nothing more than the surface integral of a vector field over a closed surface. Kind of like the flux in the plane was just the line integral, but taking the component of the force that was pointing in the normal direction. Or in other words, it was the amount of the vector field that's flowing out of the curve. And here we can think about it exactly in the same way. So the flux, if I have a region, like if I have a little piece of pipe, the flux out of the pipe, if the pipe's carrying water, is just the amount of water that flows out of that surface. And so if there's some kind of source inside this region, then you can imagine the flux is going to be great. It's going to be positive. There's going to be outflux. But if there's a sink or a hole inside the surface, then water's going to be flowing in. There's going to be a lot of influx or negative flux. So the idea of flux over a surface really is analogous to flux over a curve in the plane. Okay, so now that we've introduced the concept of flux over a surface, we're ready to state the divergence theorem. And you can almost fill in the blanks, because remember that the flux version of Green's theorem said that the flux integral was equal to the integral of the divergence. And that's going to be exactly the same thing here. So the statement of the theorem, let's introduce a little bit of notation. So we're going to have a volume region, and I'm just drawing it as a cube. So the volume region is R, the surface of the volume region is S. I have a vector field F, and what we're going to say is that the flux out of the surface, so that's F, and then we take the component along the normal direction, and then over a small surface element, is equal to the divergence added up over the entire volume region. Okay, and the interpretation here is exactly the same as in the plane. So if I look at each point, I can measure the divergence, or how much this is spreading out of that one point, And somehow if I add up the divergence at each point, that's essentially going to tell me how much of the field is flowing out of the surface of the region. Like that. So it really is analogous to Green's theorem for flux. And again, you can think that inside this region, if you have sources, so in the case of an electric field, if you have electric charge, it's going to create a divergence at points inside the region. That's going to create electric field that's has an outflux of the surface. If it's water, if you have sources, that's going to create divergence in the points inside the region, and that's going to create outflux, etc. So the divergence theorem, it's really not saying anything new, but again, it's just taking that jump from, a region bounded by a curve in the plane to a region bounded by a surface in space. And again, both Stokes' theorem and the divergence theorem are taking something that's a little bit more complicated, so a surface integral, and converting it into something easier, or vice versa, right? So this is taking a surface integral, turning it into a triple integral, which we like a little bit better. Remember, Stokes' theorem was turning a line integral into a surface integral, or it could go the other way as well. But these theorems are really just, again, relating back to the fundamental theorem of calculus. It's all about relating some sort of derivative on the interior to kind of an antiderivative on the boundary. All right, so we want to apply Stokes' theorem to compute this line integral, or this circulation integral in space. And so we see that C is the boundary of the surface given by the piece of the plane, given lying within the cylinder, x squared plus y squared equals 4. So our region is going to look like an ellipse. It's going to be, kind of taking a plane and cutting a cylinder. And so our boundary curve C is going to be here. And then the region inside, or the surface, is going to be S. And now the orientation is going to be upward. So from viewed from above, the curve is going to have a counterclockwise orientation. Alrighty. Okay, and so the first thing we need to do is remember what Stokes' theorem says. So Stokes' theorem says that we can convert this line integral, or circulation integral, to a surface integral of what? Of the curl of the vector field. And we take the component of the curl that's pointing in the normal direction of the surface over all of the surface elements. So first things first, let's parameterize the surface. Now notice that x squared plus y squared is 4, so I'm living within a circle of radius 2 in the xy plane. So that's kind of a hint to tell me I probably want x and y to be s cosine t and s sine t. Essentially just polar coordinates. And then z is x plus 4. Well, x is s cosine t, so this is going to be s cosine t plus 4. And this will be for st in the rectangle 0 to 2, so that's just the radius of the circle in the xy plane. And then t is like theta, so going from 0 to 2 pi. So let's find the partial derivatives. So that'll be cosine t, sine t, and then cosine t, partial with respect to t, will be minus s sine t, s cosine t, and then minus s sine t. And then the cross product is going to be s sine squared t minus s cosine squared t. Then we have minus, but really plus, s sine t cosine t, and then this is going to be minus, but plus s sine t cosine t, again, so that's going to be 0. Then finally we'll have s cosine squared t, and then plus s sine squared t. Okay, and that looks pretty good. Let's see. Sine squared t. This is actually, I'm sorry, this is going to be minus 2. Just double checking. So this was minus s sine squared t and then minus s cosine squared t. So this actually simplifies. So this is just s and this is minus s. So we have minus s, 0, s. All right, and then what about the curl of the vector field? Well, let's write what it is so we can practice. So we have I, j, k, partial with respect to x, y, and z. So I'm just going to put partial x, partial y, partial z for short. And then we have the x component, which is 2z, then 4x, then 5y. Okay, so this is going to be partial with respect to y of 5y, so that's 5, minus partial with respect to z of 4x, that's 0. Then we have partial with respect to x of 5y is 0, and then minus a minus partial with respect to z of 2z, which is 2. And then finally we have partial with respect to x, so 4, and then 0, so 4. Alrighty, so we have minus s, 0, s, and 5, 2, 4. And we just need to take the dot product. So our integrand is really going to be, for our surface integral, minus 5s and then plus 4s. So this is just minus s. Well, that's really nice. So now we're ready to set up the surface integral, which is just going to be the double integral over s and t. So s goes from 0 to 2, t goes from 0 to 2 pi. So this is what our original line integral is equal to. The integrand is minus s. Then we have ds, dt. So this is minus s squared over 2, evaluated from 0 to 2. So that's just going to be negative 4 over 2, so negative 2. And then this is just negative 2 times 2 pi, so negative 4 pi is equal to the value of that line integral. And we evaluated it using Stokes' theorem. We converted the line integral to a surface integral of the curl and found that the value is negative 4 pi. Alrighty, so now we're trying to find the work done by this force field. So that's just a line integral. on the particle moving along the boundary curve of this surface. So it's the piece of the sphere, looks like a radius 2. Let's sketch the region real quick. So here's 1, 2, 1, 2, 1, 2. Okay, so that's kind of what the surface looks like. It's just the kind of part of the sphere of radius 2 that's lying in the first octant, like that. And now we're giving it kind of an upward orientation, which means that viewed from above, if we look at the boundary circle, which is right here, it's oriented counterclockwise, like that. Okay, and we want the work done as the particle moves along this path from there all the way around. Okay, so what we really want, if this is our curve C, and then our surface is S, so the work done is this line integral over C of the vector field in the tangent direction. But we want to use Stokes' theorem and actually solve this integral as a surface integral. So Stokes' theorem says that this is the surface integral over the surface that this curve is bounding, this little piece of the sphere, of the curl of the vector field. Like that. All right, and then adding up over surface elements of d sigma. So the first thing we need to do is parameterize the surface. But this is part of a sphere, so we're going to recycle our parameterization of the sphere. So recall this sphere has radius 2, so rho is going to be 2. So this should be 2, and then sine s cosine t, 2 sine s sine t, and then 2 cosine s, but the range for s and t well, phi is just going from 0 to pi over 2, and theta is just going from 0 to pi over 2. It should be a parentheses really right there. So my pairs s and t are living in this rectangle, in the ST plane. All right, so let's get to work on setting up our surface integral. So we need to take the partial with respect to s, which is going to give us 2 cosine s cosine t, and then 2 cosine s sine t, and then negative 2 sine s, and then partial with respect to t is going to be minus 2 sine s sine t. Here we'll have 2 very easy to make mistakes with all these sines and cosines. This should be sine. Oh no, I was right, that's cosine. What am I saying? let's see, this is going to be sine s. And then cosine t. And this is actually going to be 0. Alrighty, let's take the cross product to find the normal direction, pointing outward. Okay, so we have 0 and then minus this guy, so that'll be plus 2 sine squared s cosine t. And then let's see, here we have 0 and then times this, so this will be, let's see, but it's, okay, so it's minus this, but the whole thing's minus, so it'll be 2 sine squared s. And then looks like sine t. And then what do we have? We have actually, oh, you know what? These should be 4, shouldn't they? 4 and 4, because 2 times 2 is 4. And then here we have 4. Looks like we get a cosine squared t. Yeah, so let's do this. So this is going to be 4 cosine s sine s. And then we have cosine squared t, and this is going to be plus 4 cosine s sine squared t. So the whole thing is going to be 4 cosine s sine s. Alrighty. So the next thing we need to do is find the curl of the vector field. So in this case, the curl of f is equal to, well, let's see, I, j, and k, and then we have partial with respect to x, partial with respect to y, partial with respect to z, and then the component functions p, q, and r, where here's p, here's q, and here's r. Alrighty. So what do we get? We have partial of x here, so that's going to be 2x, and then minus this partial y, that's 0, and then minus this, 0, minus this, it's going to be 2z, and then partial of x here is going to be 2x again. Nope. Actually, this is going to be 2y, it looks like. Yeah, so 2y minus 0, and then 2z, and then 2x. Yep, that looks good. Okay, so we can actually evaluate this at y, z, and x, the various parameterizations. So this is going to be 2 times 2, so 4, this will be sine s sine t, and then this will be really 4 cosine of s, and then this will be 4 sine of s cosine of t. And recall that what we had from rs cross rt was this, 4 sine squared s cosine t, then 4 sine squared s, sine t, then 4 cosine s sine s. Alrighty. Now we just need to actually do this dot product and take the integral. So the integral is going to be from 0 to pi over 2 for both of the angles. And when we do this, notice we're going to get a lot of 16s, so we can factor out a 16. And then what do we get here? We get sine cubed s, then sine t cosine t, plus sine squared s cosine s sine t. All right, and then let's see, what do we have here? We have sine squared s, and then cosine s cosine t. And we'll just do ds dt. That is dt. Okay, so now we just have a bunch of trig integrals to solve. And this really isn't so bad. And the cool thing is that this entire integral ends up just equaling 1. So the final answer is just 16. And just for brevity, I'll just leave it kind of up to you to work through all of this. But you know, this is mostly just a lot of u substitutions. Like here you want to let u be cosine s, here you want to let u be sine s, here you want to let u be sine s, etc. And the final answer is 16. So that's the work done by this force field on the particle moving around this particular boundary curve. And again, we solved this by using Stokes' theorem and evaluated the line integral along the boundary curve as a surface integral over the surface. Alrighty, now we're going to apply the divergence theorem. And the good news is that the divergence theorem is a little bit easier to apply because you're not converting a line integral to a surface integral. You're actually converting a surface integral to a just good old-fashioned triple integral. So let's see how it works. So recall that the divergence theorem here says that we can replace this sort of crazy surface integral, where S is going to be the boundary of this cube, or in other words, this is the flux of the vector field out of the cube. We can replace this with the triple integral over the volume region, but the volume region is a cube, so actually my limits just go 0 to 1, 0 to 1, 0 to 1. But now what I integrate is actually the divergence of the vector field. Okay, so what's the divergence of the vector field? Well, I just take the partial of this with respect to x, which is 0. I take the partial of this with respect to y, which is 9x squared z squared. And I take the partial with respect to this of z and add that, but that's also 0. So this is just dx, dy, dz. And look at that. This is amazing. I mean, the Stokes theorem applications just involved, some technical details. We had to parameterize a curve, etc., etc. Here we don't have to do any of that because we're just converting the flux out, which is a surface integral, to a triple integral over the divergence. So the divergence theorem is really just a beautiful theorem. I mean, if you tried to do the flux over this cube, it might take you a few hours to do. I mean, you should never do that. This is the point. You should convert it to a triple integral. Okay, so what do we get? I mean, this is not so hard. This is just going to be x cubed over 3, so that's just going to leave me with 3x cubed z squared from 0 to 1, which is just 3. And then I integrate z squared, that just leaves me with 1 z cubed, evaluated from 0 to 1, but that's just 1. And then I just have this is just y evaluated from 0 to 1. So the final answer is 1. And that's really cool because we can think about that's the flow rate or the flux of this vector field out of the cube. And we found it by just doing the surface or the triple integral of the divergence. And so somehow we were just adding up kind of you can think about it like as the charge distribution inside the cube or the gravitational distribution, and just measuring that as a divergence, and it was just giving us the flux out of the region, which is just 1. Alrighty, so again, what we're looking for is the flux out of this region, or across this surface, that's the boundary of this region, of this vector field, which is technically a surface integral, but we don't want to do that. That's hard. So what we do want to do is convert this to a triple integral of the divergence. And so the volume region, we'll call R, we'll describe in a second. It's going to turn out to be a little bit easier to describe in cylindrical coordinates, but we'll get to that. But we're just integrating the divergence. And so what is the divergence? Well, partial with respect to x of this is 0. Partial with respect to this is 2y. So that's 2y. And then we just have dv. And like I said, this region, I think we want to describe in terms of cylindrical coordinates. So z, first of all, is going from 0 to y minus 3. Now in polar coordinates, y is r sine theta, so this is really r sine theta minus 3. And that's 2y dz. And then r goes from 0 to 3, because the projection onto the xy plane is just a circle of radius 3. And then theta goes from 0 to 2 pi. And don't forget that we actually have an r dr d theta. And the 2y, we can actually replace, put in polar coordinates, as 2r sine theta. Alrighty. And so this is the integral 0 to 2 pi, 0 to 3 of 2r sine theta times r sine theta minus 3. And then we have another r dr d theta. All right. So here we have a r squared, and then another r is actually an r cubed, and here we'll have an r squared. So this will be, this first term will have an r cubed, so that'll be r to the fourth, 2r to the fourth over 4, just r to the fourth over 2. Then we'll have a sine squared theta. And then we'll have a r to the third divided by 3 times 3, so just 1, sine theta. And then that's evaluated from 0 to 3. d theta. Okay, so this is just going to be, well, 81 over 2. This is actually going to be 0. Now it's really going to be 81 times sine theta, but when I integrate sine theta from 0 to 2 pi, that's going to give me 0. So I'm just going to have the integral of 81 over 2, 0 to 2 pi, sine squared theta, d theta. But now the integral of sine squared theta from 0 to 2 pi is something I'm sure you've seen before. So we can use the power-reducing trig identity and make sine squared equal to 1 minus cosine 2 theta over 2. And when we evaluate that from 0 to 2 pi, we just get pi. So the final answer is 81 pi divided by 2. And so that's the flux through this cylindrical surface. And we found it by converting the surface integral to a triple integral using the divergence theorem.